Hey everyone, welcome back to another step in our Solidity from Zero Explainer series. This explainer is proudly brought to you by Forge College. Today we've got a seriously foundational and honestly pretty fun topic lined up for you: function parameters and the memory model. If you've ever found yourself wondering how smart contracts actually handle the data you feed them, well, you're in the exact right place. We're going to decode how Solidity manages data behind the scenes. Trust me, it's like a giant puzzle, and it's incredibly satisfying once you see how it all clicks together.
Okay, so here's our roadmap for today. First, we'll look beyond function visibility. Second, we'll break down the 3 data locations. Third, we'll talk about photocopies, blueprints, and envelopes. I promise that'll make sense soon. Fourth, we'll dive into real-world gas and mutability. And finally, we'll wrap up with your next steps. Let's get right to it.
All right, part 1, beyond function visibility.
If you were with us for the last lesson, Function Visibility Fundamentals, you know we solved a major puzzle, figuring out who was actually allowed to call our functions. Setting things to public, private, or internal. That's visibility. But today we're shifting gears. We're looking at the memory model. Basically, once a caller gets past the bouncer and is allowed inside your function, what on earth happens to the data they bring with them under the hood?
Well, here's the core rule of thumb. Symbol data, things like a basic number or a Boolean, that stuff is just copied by value. It's super lightweight, so Solidity just makes a quick copy and moves right along. But complex, dynamic data, stuff like arrays or long text strings, that's heavy lifting. You can't just toss that around willy-nilly. It requires explicit instructions from you, the developer, on exactly where it should live while the function is doing its thing.
Which brings us nicely to section 2, the 3 data locations.
First up, we have storage. Think of this as the permanent record. When you declare a parameter as a storage reference, it's pointing directly at a variable that's saved permanently on the blockchain. The huge, absolutely crucial takeaway here is that if you modify a storage parameter, you are literally changing the persistent state of your smart contract forever. It's incredibly powerful, but yeah, it comes with a lot of responsibility.
Location number 2 is memory. Now, unlike storage, memory is a totally temporary, fleeting space. It exists only for the duration of that specific function call. When you pass a dynamic type as memory, Solidity drops a temporary copy into this space. You can tweak it, manipulate it, do whatever you need to do, but once that function wraps up, poof, all those changes vanish. Nothing gets saved to the blockchain.
And finally, there's call data. This one is kind of special. Call data is an immutable, completely read-only view of the data that an external caller sends in. Because you can't modify it, Solidity doesn't even bother making a copy. It just lets you look directly at the original input. This makes call data insanely gas-efficient for your external functions.
So as you can see, developing in Solidity is essentially a balancing act. You're constantly weighing gas costs, mutability, and visibility against each other. Need to change the state directly? Use storage. Need a temporary sandbox? Go with memory. Or maybe you just need to read an external input as cheaply as possible. In that case, calldata is absolutely your best friend.
Let's move on to section 3, photocopies, blueprints, and envelopes.
Now, if all this sounds a little too abstract or overly technical, let's ground it with a really simple office analogy. Imagine you're working in an engineering firm. Memory is your photocopier. You take the original document, run it through the copier, and take the copy back to your desk. You can doodle on it, spill coffee on it, the original is totally safe. Storage, on the other hand, is the master blueprint pinned up on the main wall. If you walk up to that blueprint and make an edit with a marker, everyone sees it. You've permanently changed the official record. And calldata? Well, that's a sealed envelope. You can hold it, you can look through the clear window to read exactly what's inside, but you absolutely cannot break the seal or alter the contents.
So, whenever you're designing a function and trying to pick between these data locations, just ask yourself this: do I need to doodle on this safely in my own isolated space? Or do I actually need to permanently update the official record? If you just need a safe doodle space, use a memory photocopy. If you need to update the real deal, access the storage blueprint.
All right, section 4, real-world gas and mutability.
Let's put this into practice and see how these choices affect real smart contracts. Imagine we're building something called the approvals contract. The entire goal of this contract is to maintain a stored list of approved wallet addresses. And we want to build functions that let us append new addresses from an input array right into our permanent list. So let's map out the runtime path of 2 different ways an external caller might do this. Say we write a function called add first memory.
The moment someone calls it, Solidity physically copies their entire array into memory. If they send a massive array, that photocopy costs a ton of upfront gas. On the flip side, what if we use add first calldata instead? Now the contract just reads straight from the sealed envelope. No copying occurs, which means it costs way less gas. In both cases, we end up grabbing the first element and pushing it to storage. But the journey to get there? Totally different gas bills.
Now, let's zoom in on what happens when we're working purely inside the contract. Imagine an internal helper function called replaceApproved. When we pass a storage reference into this helper function, we aren't making a copy. We're passing an alias. It's like a direct laser pointer straight to the on-chain data. Any mutation we make inside that internal function instantly updates the permanent blueprint. It's blazingly fast for making in-place updates, but you've got to be super careful.
So here is the real-world contrast. Making a photocopy in memory costs you upfront gas to create, but it's totally safe to play around with and discard. Editing the blueprint in storage, though, that's incredibly fast for direct access, but any edit changes permanent state, which incurs heavy, persistent gas costs. It is a constant architectural trade-off that you'll be managing.
Let's wrap this up with Section 5, your next steps.
So, the crucial point is this. If you only remember one thing from today, make it this quote. Default to calldata for external read-only inputs, use memory for temporary manipulations, and use storage for immutable, alias to persistent state. Seriously, internalizing that one sentence is going to save you countless headaches and a whole lot of gas fees as you grow as an intermediate Solidity developer.
Let's do a rapid-fire recap to lock this all in. 1. Always declare explicit locations for your dynamic types. 2. Calldata is your immutable, extremely gas-efficient best buddy for external inputs. 3. Memory is your safe, temporary sandbox to manipulate data without consequences. And 4. Storage, aliases your permanent state. So treat it with respect because it updates the blockchain directly.
So here's a provocative question to leave you with. Now that you know how to safely manage and route the data within your functions, how will you combine this with what we learned about visibility to build truly secure smart contracts? Well, we are going to answer exactly that in our next lesson, implementing visibility in practice. Make sure to head over to forge.college to dive into that lesson and to explore all the other incredible Web3 topics we have. Remember, this explainer was proudly made by Forge College. Thanks for joining me on this deep dive into the memory model, and I'll see you in the next one.